So I'll talk a bit about the role of convexity in optimization, and we already looked at this a little bit in terms of what it means for solvers. So here I'll give another concept, which is duality. That's also very important. So we're going to distinguish convex and non-convex mixed integer nonlinear optimization problems. And the definition is there's a slight abuse of notation or terminology here. So I'm going to use the term convex min-low, which is not really a good term, but it's the best that we know. So there's again the definition of convexity, which is the function is convex, a differentiable function is convex if it lies above its supporting hyperplane. So on the right-hand side, again, you have a supporting hyperplane, a first-order Taylor approximation around x0. You plug any value x1 into this hyperplane, and then the original function value at that point x1 is larger than the function value there. So we're going to talk about a convex min-low if the problem functions f and g are convex functions. And if either f of x or any of the gi of x is a non-convex function, then we call the min-low non-convex. And so this is some abuse of terminology, and somebody should ask this question: what do you mean by a convex mixed integer nonlinear optimization problem? So here is the feasible set of this is an integer linear optimization problem. So I have two integer variables, y1 and y2, and the red dots are the integer lattice points. So those are the integer points. And then I have the blue feasible set. There's two linear or affine constraints that limit my linear set. But if I look at this problem, then the feasible set is just a collection of these red dots that lie inside the blue region. And so clearly this is not a convex set, because if I take a convex combination of two of these points, then the line joining these 2 points is not a feasible point. It's not an integer point. So the integer lattice that's drawn in red here is always non-convex. But the continuous relaxation, if I just forget that I have integer points, that is a convex problem. So the blue set here is a convex set. And the linear functions are convex. So in this case, that will be a convex set. So what we mean by convexity then is we, for the time, ignore the fact that we have integrality constraints, and we talk of the problem as being convex if its problem functions are convex in this expanded space. So you have to replace the integrality by real variables, the integer variables by real variables. And then it makes sense to talk about convexity. And so we defined the convex hull of a set as being the set of all convex combinations. I take 2 points inside my set, any 2 points, and I join them up, and the line that's in these 2 points is the convex hull. So that's this definition that we saw in the last lecture. And here's a number of simple examples. So for example, if I have the integer lattice with lower and upper bounds on my variables, then the convex hull of this set is just the integral between L and U, the lower and the upper bounds that I have on my integers. Finding this convex hull is really hard, and it corresponds to almost solving the problem. But it's very important in mixed integer linear optimization because I can solve, there's a theorem that says I can solve a mixed integer linear optimization as a continuous linear optimization problem over the convex hull of the feasible sets. And I have a proof by picture, so this is not a formal proof. So here's again the picture that you saw earlier. This is the feasible set of an integer linear optimization problem. The red dots are the integer lattice, and the green region is the convex hull of the feasible red dots. And now if you take any linear function that you minimize over the set, the linear function is just a straight line. If you minimize it, you find an integer point. If you choose a different angle, you will always land, or one of the solutions will always be at a vertex or an extreme point of your convex hull. There's always a solution to the linear optimization problem that lies on the extreme, that's an extreme point of the convex hull. There could be infinitely many solutions to a linear problem. So for example, if I took an objective function whose contours are parallel to this line here, then any point joining those 2 points would be an integer, would be a linear optimal solution, but only the 2 extreme points are integer optimal solutions. But they're usually easy to reconstruct, and we can detect that. Now, the same is not true for mixed integer nonlinear optimization. So in mixed integer nonlinear optimization, even if you give me the convex hull of the integer feasible set, that's not enough for me. So here's a very simple example. I'm minimizing over y, just this simple quadratic, which is yi minus a half. So the solution, yi is between 0 and 1. The solution of the relaxation, the continuous relaxation, is just yi equals to a half for all yi. So this is this picture here. So if I have 2 variables, there are 4 feasible points, 0, 0, 0, 1, 1, 1, and 0, 1. And the contours of this objective are just drawn by these dashed lines. And if I just minimize this function over the convex hull, I would still get a point that's in the interior. And so I don't have that nice result that I had for linear optimization. But there's a trick that helps us, and the trick is to add an objective variable. So we're going to transform this problem. I should have written this down. The problem that's written here into a new problem, where instead of minimizing f of x, we now have an additional variable, eta, x and y, and we minimize eta subject to eta greater or equal to f of x and y, and 0 greater or equal to g of x and y in an integer. So I introduced one additional continuous variable, and now I'm always minimizing a linear function over a possibly nonlinear feasible set. But if I can replace this feasible set that I have down here by its convex hull, then the linear function will then pick up an extreme point. So this is a very important transformation, and we're going to use this throughout for our algorithms. So I'm going to assume from now on that my objective function is linear. And I can always do that. If I have a nonlinear objective function, I have one additional variable that I need, and I throw it into the constraints. Okay, so once we have convexity, there's this really useful concept of duality. So I'm going to introduce duality for convex and non-continuous convex optimization problems. So again, I'm dropping the integer variables because it's much harder to introduce this concept in the integer case. So then I have a problem P, which I call the primal problem. So P stands for primal. And I can construct a dual problem. And in this case, this is the Wolf dual. There are many equivalent or similar dual problems. And there's a theorem that says that if I have a solution to my primal problem, then there's also a solution to this dual problem here, which is written in terms of the Lagrangian of the original problem. So L is the Lagrangian function, which introduces Lagrange multipliers or dual variables or reduced costs for my inequality constraints. And in fact, the maximum of this dual problem is the same as the minimum of my primal problem. And so this is a very nice property because it means that if I find any feasible point to this problem, not necessarily the maximum, but a feasible point, then this feasible point will be less than or equal to the maximum, which gives me a lower bound on my objective function of the primal problem. And that's used in pruning and integer optimization. Now, a warning here, this Wolf dual is not in general a convex problem. And the reason is because I have these potentially nonlinear equality constraints that I introduce here, which are the first order conditions of my original problem. So that's a nonlinear set of equations, or can be a nonlinear set of equations, and so that's not always convex. Okay, so there is this primal dual pair of these two problems that go together. The primal problem is our standard continuous convex optimization problem, and the dual problem is this second problem that we have derived by introducing the Lagrange function. And the reason we have dual problems is that sometimes they're easier to solve. They can have fewer constraints. And the second reason is that any feasible point, not necessarily the maximum, but any feasible point will be a lower bound on the primal optimal solution. And that plays a very important role in limiting the search that we do for integer optimization problems later on. So I have a few examples of the dual problems, and you've probably seen some of them before. So there's this linear optimization problem or linear program in standard form. In this case, I have two sets of Lagrange multipliers. I have multipliers lambda for the equality constraints and mu for the inequality constraints. And so the Wolf dual, this is just the formula for the Wolf dual. There's no inequality on the, so there's no, the multipliers of equality constraints are not constrained to be non-negative, only the inequality constraints. You can actually write this down. You can write this down more compactly. So the Lagrangian function and the Wolf dual are given there. And so what I need to do is I need to put in the functional forms that I have for my original problem. So if I take the gradient with respect to x of my Lagrange function, which is the first line up at the top, then I differentiate with respect to x. I get c minus A transpose lambda minus mu. The b term vanishes because it doesn't depend on x. And so one of the conditions of the Wolf dual is that that has to be 0. And I can write this equivalently. I can solve this equation for c. So for mu, I solve this equation for mu. Mu is just c minus A transpose lambda. And I had the constraint that mu is greater or equal to 0. And now I can actually use this condition here by substituting mu. I can simplify my objective function. So in the Wolf dual, I'm maximizing the Lagrangian. So I substitute mu into my objective function. So it goes here at the very end. That's the mu that I substitute here. And now you can see that you have these two terms, c transpose x, that cancel. And there's a minus lambda transposed ax. And here there's a plus A transpose lambda transposed x. And so those two terms cancel as well. And so my objective function then simplifies to lambda transpose b. So what I have is, if I put all this together, you have the Wolf dual now is maximizing lambda transpose b. That's my objective function that I just transformed. I eliminated this constraint here, and I'm going to write it equivalently as c minus A transpose lambda greater or equal to 0, and then I don't need the mu's at all. So that's the primal dual pair that I had on the previous board. So there's at the top is the primal linear program in standard form, and the bottom is the dual linear program, the corresponding dual linear program. And I've just rewritten it slightly. Instead of lambda transpose b, I've got b transpose lambda, and I rearranged the inequalities. And so any feasible point, any lambda that satisfies this inequality, if I evaluate b transpose lambda, then I get a lower bound on the objective function of my primal. And depending on the shape of A, this could be easier. It might be easier to solve this problem sometimes. You can also form the dual of a linear program that's not in standard form. So you do the same thing, right? You introduce multipliers, lambda for the inequalities and mu for the simple bounds. You write down the Lagrange dual. You evaluate this. You take the gradient of the Lagrangian, set it to 0. You get some inequalities that pop, or equations that pop out that allow you to simplify it. And the nice thing about this dual is that it looks very similar to the first one. So there's both problems have simple bounds that are greater or equal to 0 on their variables, lambda. They both have a linear objective, and there's a sort of a lambda less than or equal to c, and an a transpose x greater or equal to b. So that's sometimes called a symmetric dual, and it has a nicer form. You can do the same for a quadratic optimization problem, assuming that the Hessian is positive definite, so that you can form the inverse. You can then use that to eliminate the primal variables, and you get a very simple looking problem. So those are just things that you can do. The nice thing about this problem now is that this dual problem only has simple bounds, and we can solve problems with simple bounds much, much easier sometimes. But the price that you pay is that you need to operate with the inverse here, or you need to factorize the matrix G. And typically what happens when you do that is when you factorize G, then this term here, A transpose G inverse A, will be a completely dense matrix. So the original problem could be sparse, meaning it has a lot of non-zeros in its matrices. The dual problem will be completely dense, but it has a much simpler structure. And so, for example, you can do projected gradient methods to solve this problem potentially more effectively. But it involves the inverse or factors of G. So whenever I write down an inverse, I would not ever form an inverse. You would form a factorization of that matrix G and then operate with those factors. Okay, so this is kind of a useful concept, duality. The duals also give us information about the constraints that are active in the original problem. So for example, if I know that I have a dual solution that lambda I star is greater than 0 for some particular index I, then I know that my Gx has to hold with equality. And that comes from the first order conditions of the nonlinear optimization problem, which says that if my multipliers are positive, then the inequality has to hold with 0. There's a nice little exercise that you can do if you have a quadratic optimization problem where G is the identity matrix, and you actually get out a very simple dual problem. If you go back to the previous page, if you have the identity matrix, then the inverse of the identity matrix is the identity matrix. So this becomes a much simpler problem, potentially. Or it could be a multiple of the identity matrix, and again, you can invert diagonal matrices very easily. And then I've said this many times now, the dual gives us a lower bound on the primal optimum. So we use this in mixed integer optimization to cut off branches or solutions of the tree that we don't want to search. So that's sort of one reason why duality is important. And so I talked a little bit about convexity. And the takeaway points are really, convexity is our friend, and convexity helps us. Examples of convex problems are linear optimization problems or quadratic optimization problems with positive semi-det Hessian. Now, in practice, many problems are non-convex, and so we still have to cope with that. The nice thing is that we can often solve convex problems to global optimality. And in fact, the nonlinear optimization solvers, they will give you a guarantee that they will find the global optimum in that case, provided there's some stability assumption that holds. And then Pietro is going to talk about more favorable complexity results, and we'll talk about algorithms later. It also plays a very important role in terms of designing algorithms. If I have convex sets, then I can approximate convex sets by cutting planes, for example, because I can always find supporting hyperplanes. And we'll use that in one of the algorithms later that we're going to talk about. And duality is this nice transformation for convex problems that creates a new problem that can give us potentially lower bounds that we can use to prune nodes to eliminate search space in our branch and bound tree search. Okay, so this was maybe very fast, but we're back on track, and I'll let you ask some questions, and I'll try to answer them. Yes?
I have a primal problem and minimizing. Converting dual converting into maximization. Why?
Oh, okay. Why is it? Why am I maximizing? Let's see if we can. Okay, so the primal problem is a minimization problem. The dual problem is a maximization problem. It's okay. So I'm looking at, in the dual problem, I'm looking for a stationary point, and I don't have a good answer for that, actually.
So you basically have a relaxation. So you take the original problem, you want a relaxation, you get a relaxation. This is what the L function gives you, right? And the relaxation gives you a lower bound.
Right. So the Lagrangian is the original objective function minus plus lambda transpose g of x. And so lambda is non-negative, g of x is less than or equal to 0. So this term here is less than or equal to 0, right? Because lambda is greater or equal to 0. So,
The whole term, sorry. Yeah, exactly.
yeah. So then this whole term, as Ashutosh pointed out, is then less than or equal to f of x. And so now I'm looking for the solution where these two are the same. So I'm driving my solution up from the bottom. I really don't have a good answer for that. Nobody ever asked me that question. So,
Since, I mean, this is the main idea, really. You have a lower bound on f of x, and you want to get the best possible lower bound. So you want to maximize the function.
Yeah.
To get, and with convexity, you actually match.
Yeah.
With non-convexity, no.
Yeah. Sorry? Yes, we haven't talked about constraint qualifications. I said something like stability assumption, and that's a constraint qualification. So a constraint qualification is a condition that means that the feasible set locally looks like an affine feasible set. That's one way of thinking about a constraint qualification. So what we want to avoid is situations where we have a cusp, a feasible set that looks like this, because in this case, at this point here, the gradients of these two constraints are linearly dependent, and they don't provide us any information as to what happens in this direction here. So I omitted constraint qualifications, and I'm not going to talk about I'm happy to answer lots of questions about constraint qualifications. I love constraint qualifications. I can talk about Mangasarian, Fromovitz ad infinitum, and they play a very important role. But I was trying to avoid talking about constraint qualifications here. But we can have a discussion about that. There's important classes of problems where constraint qualifications are violated. For example, Stuckelberg games, leader-follower games, when you write them down as optimization problems of equilibrium constraints, any feasible point violates a constraint qualification. And they sometimes cause problems for solvers. In this case here, the constraint normals look like this, so they're linearly dependent. And that causes issues for optimization solvers that locally linearize the problem and then try to compute a step. So I haven't talked about how to solve these problems yet, but our main method for solving these problems will be some form of Newton method where I linearize the problem or do a local approximation and then solve that to get a step. And if I don't have a constraint qualification, then those methods typically fail. Do you know other things that happen, bad things that happen if you don't have constraint qualifications? Let's see, who knows what bad things happen without constraint qualifications? Anybody? Okay, if you don't have a constraint qualifications, your multiplier set is unbounded. And these multipliers can blow up to infinity. Again, not good if you're solving these things numerically. If you don't have a feasible point, so far we've always been talking about we always have feasible points. If you don't have a feasible point, then the minimum, there's a kind of point that is the minimum, the least infeasible point. And that point automatically violates constraint qualifications. But we can deal, that's one we can deal with. I tried not to talk about constraint qualifications. So show of hands, who has heard of Mangasarian Fromovitz constraint qualification? Okay, that's a few. Linear independence constraint qualification. That's an easier one that just says you form the Jacobian of your matrix G, and for the active constraints, they're linearly independent. And there are lots of constraint qualifications, but I'm sorry, I'm not going to talk about constraint qualifications. They're very important.
So if primal is non-convex, can dual help in some?
If the problem is non-convex.
If the primal problem is non-convex, can dual help in some?
It still gives me a lower bound, but now there's a gap. There's potentially a duality gap between the solution that I get here. This will be strictly less than the solution that I compute here. So it's not clear that how much the dual can help in that case. Yes. What would you like?
That you added one variable there.
I added one variable. You would like that to be explained again? Okay. I can do that. That I can do. So here's something I know. Thank you for asking a question to which I know the answer. So if I don't add this eta, so here there's eta is coming out of the board here. That's eta. If I didn't have this eta, then this example shows that even if I know the convex hull of these 4 points, so the convex hull of these 4 points is just the box that connects these 4 points. Even if I know the convex hull, if I solve this relaxation, I can find a point that lies in the interior. But if I now lift this problem and I introduce this additional variable eta here, then I get a problem that now has a linear objective function. And so if I can somehow magically find the convex hull of my feasible set, And I can do that, and we will work on algorithms that will try to find the convex hull of this feasible set. Then I can solve this mixed integer nonlinear problem by first finding the convex hull magically, and then solving a linear problem over the convex hull. And some of the algorithms we'll talk about will do that. They will try to iteratively find this convex hull by chipping away parts that are not belonging to this convex hull. But I can't do that same trick if I keep my nonlinear objective. So whenever I have a nonlinear objective here, I might end up in the interior. And this is the one example that tells you why there's this slight difference. But it's not really a difference. All you need to do is assume that you're mixing into a nonlinear optimization problem to test this additional variable. And so what does this variable eta do? I'll do it over here. I'll draw a quick picture. Let's assume I have a problem with just one variable, f of x, and it doesn't have to be convex, and I want to minimize f of x. Then you can find the global minimum is there. I can also write this now as minimizing eta subject to eta lying above the function. So what does that mean? I now I relabel my y-axis as eta, and I'm now trying to push eta as far down as possible, but I must lie above my function. And so I end up in the same point, right? That's the lowest eta that I can get. If I push eta lower, then there's no longer an x for which this holds. So that's the transformation that I'm doing there. And this works in many dimensions the same way. Excellent question. We needed another picture here. Thank you.
When we transform the primal into dual,
Yeah.
so generally we are setting or we are telling that the dual gives the lower bound for the prime. But what is the relation with the space variables, that variables of the primal and dual?
Oh, okay. So that I think is in. There's the theorem. So we transform the primal to the dual problem. So down here is the dual problem, and it's the same variable. So the same x star. So x star is the variable that solves the primal problem at the top, and that's also part of the solution of the dual problem. And then there are these multipliers lambda star that come into effect. That basically the lambda star ensure that a first order condition holds here. So this condition is, I've sort of abbreviated it here. Basically says that I can write my the gradient with respect to x of my Lagrangian, that's the gradient with respect to x of my objective function plus the sum of lambda I times the gradient of all gi of x. So that means one way of thinking about this is that I can write this as a negative combination of gradients of the Lagrangian. I have a picture in the next lecture that illustrates that a little bit. And these lambda i's are the optimal multipliers that tell you also what constraints are active.